All right, good morning, folks. There's a few people joining us online. If you are online, just leave, please, just a quick note in the chat if the sound's okay. It looks okay from my side, but you never know what you guys experience. What we're going to do today is fit in as much as we can. We're going to do kind of a bit of a run through out of all of the reactions and mechanisms that you are responsible for from units 8, 9, and 10. And this is being recorded as well, so you will be able to see it later. The link's up already on Acorn. So let's get started right away. All of the reactions from Unit 8 are addition reactions. Well, I guess you could argue the cleavage reactions aren't addition. But they're reactions of alkenes and alkynes, and for the most part, we're adding something to it. And the first one that we looked at was hydrogenation, hydrogenation of alkenes and alkynes, and there was 4 variations of this reaction. So I'm going to try to keep track of each one here just with a number. So if I look at the first one, this was starting with an alkene where we used hydrogen gas and we also used some metal catalyst. And the 4 that we looked at were platinum, palladium, rhodium, and nickel. So any one of those 4, let's put nickel in. And what that does is it adds hydrogen to the double bond to give you an alkene. If you do the same thing with an alkyne, you get the same thing. You get that same alkene. It'll add 2 units of hydrogen, and so you need 2 equivalents. You can't stop that halfway under those conditions. There is a way to stop it halfway, though, and that is using a poisoned catalyst, and the poison catalyst that we used was nickel boride. Well, we used nickel boride, but we also used Lindlar palladium. In fact, I think Lindlar palladium is probably the more common one that you'll see. So this would start with something like this. It would also use hydrogen gas, and it would be like Lindlar palladium, or nickel boride was another one. But most likely this one. That'll give you an alkene, and it will be a cis alkene that you get. That's because all 3 of these reactions have syn stereochemistry, which means both hydrogens are adding to the same face as the alkene. And when you add it to an alkyne, that means you end up with cis. If you had one, like if you did the first reaction with something that was cyclic, like, let's give you an example like this. If we use hydrogen here with, I don't know, let's use rhodium. Rhodium seems not to get used all that much, but it'll work. So we're going to use rhodium here. What that will produce is an alkene that looks like, or an alkane that looks like that, meaning those 2 methyls are going to be cis to each other because the 2 hydrogens that went on are also cis to each other because it's syn addition. And we looked at why that was with the mechanism, with the metal surface, and so on. But that's not a mechanism you need to draw. The 4th one, which is the last variation, was 4 alkynes. And this was using, we call this the sodium metal reduction, or dissolving metal reduction. And that's using sodium with ammonia. That takes it down to the alkene as well, but this one gives you the trans alkene. Now, these conditions, the sodium and ammonia, like that's sodium metal. You would never mistake these conditions if you were doing them in the lab with another similar looking set of conditions, which is this one. We use this one later on, as you'll see. That's something totally else. So just don't mix up the sodium and ammonia with the sodium amide and ammonia. One is a metal, and the other is a strong base. Cool. So that is the first 4 None of those reactions require you to draw a mechanism. You just have to be able to draw the product and know what it makes. The next one, 5, we did addition of HX. And this reaction is one where you start with an alkene. Let's use, I don't know, this one again. Let's put another methyl just to make it different. And what we do with this alkene is we want to add something like either HI, HBr, or HCl. And so those conditions, let's use, I don't know, HCl. What this does is initially a proton transfer. So you'll have HCl, where this double bond attacks the hydrogen, the pair moves to the chlorine, and you end up with a carbocation intermediate. And in this example, the carbocation could have ended up on either side of that double bond, but it's going to be predominantly on the carbon that gives the more stable carbocation. So in this case, I put the cation where I did because that gives you a tertiary carbocation, which is much more stable than if I added the hydrogen to the other side. So that hydrogen ended up here. There was already a hydrogen there from before, and that gives that carbocation. It also gives a chloride ion, which you may remember from Unit 6 is a good nucleophile. And what we're going to do is use that chloride to attack the positively charged carbon. And you get this. So when HX adds that way around, when the hydrogen adds to that carbon, we say that this is Markovnikov addition, where the hydrogen adds to the less substituted carbon, and then the other part adds to the more substituted carbon. This works for HCl, it works for HBr, and it works for HI. So we call this mechanism electrophilic addition, and it goes by the name ADE2. And it's just these two steps. Protonation, strong acid, carbocation capture. So there's similar steps to ones you've seen in earlier reactions. Okay, after 5, we have 6, which is hydration of an alkene. Hydration means addition of water. And if you take that same alkene as before, and usually what we use is a mix of like 50% sulfuric acid, 50% water. And now sulfuric acid is a strong acid. Water can act as a base and react with sulfuric acid. So really what those produce when you mix them together is H3O+. So what we can use as our reactant here is just going to be H3O+. I'm going to draw this over here. So we have our hydronium ion there. And then what happens is we have a strong acid. It's going to transfer a proton to the alkene, and it's going to end up the hydrogen on the less substituted side because that gives the better carbocation. It's going to look like that. Proton transfer produces this alkene plus a molecule of water. And then what we can do is have the water just go in and attack there. Water can be a nucleophile. Water can be anything. It can be a nucleophile, it can be a base, it can be an acid. I guess in extreme circumstances, it can be an oxidizing agent or a reducing agent too. But we don't really deal with that in this course. All right, so what that gives you is, yeah, I didn't add any carbons there. Oxygen, hydrogen, hydrogen. One lone pair and a plus charge on the oxygen. So we have, it's the same mechanism as before. Proton transfer to make a carbocation. Carbocation capture with the nucleophile. And then we have to finish this off by removing H plus from the product because we don't like to have final products that are not neutral. So what we're going to do is just take a molecule of water, lots around, and we're going to remove one of those hydrogens. And that's going to produce OH, just like that. This reaction, hydration, as well as the previous one, if it creates a chiral center, you'll get a racemic mixture. And the reason is when you have a carbocation, it's flat, it's sp2 hybridized, it's planar, and typically there's no preference for the nucleophile to come in either in the front or the back. And so for that reason, you get kind of like a 50-50 mix of the two. I feel like now would be a good time to jump and pull a random one out of chapter 9. How's that sound? I'm a little out of order here, but thematically this fits. This would be a reaction where, I like this alkene. Let's use this one again. We're going to react this one with HBr, and we're going to do it in the presence of a peroxide, ROOR. And so in this case, that peroxide reverses the course of this reaction. What this produces, you still get addition of HBr, but it adds the other way around. It's anti-Markovnikov, this particular reaction, because the peroxides change the way it works. And the mechanism for this we looked at in Unit 9. This starts with the peroxide, which we would call an initiator. It initiates the reaction in an initiation step. And so what we get is that bond breaks, homolysis, so one electron goes onto each oxygen. And we get two molecules of RO dot. So this is initiation because you start with something that is closed shell, something that's not a radical, and you end up with radicals. So this would be called an example of an initiation step. Then we get propagation steps, not an R, that should be a P, where you begin with a radical like that, and it's going to react with HBr. And what happens here is the HBr bond breaks, those two electrons come together, and then one electron goes onto the bromine. So you get your ROH, plus you get a bromine radical. And bromine radicals are really the sort of engine of this reaction. What they will do, bromine radicals can do all kinds of things, but what they'll do most quickly in the presence of an alkene is add to the double bond. Remember the pi bonds are weak compared to sigma? If there's going to be a reaction, it's going to be at the pi bond. Okay, so what happens is let's get our alkene in here. And we have our bromine radical. And then what can happen is, see these two arrows kind of point at each other? They kind of meet in space. That means those two electrons pair, and wherever they came from, there's going to be a bond formed between those two atoms. There's two electrons in that pi bond, so the other one goes onto the carbon. And this produces this carbon-centered radical. So that's a propagation step because you start with a radical and end with a radical. And then that thing can react with another HBr. So if you bring in an HBr, then what happens is that gets together with an electron from there, an electron from there, and you produce a molecule of your product. Plus, you also regenerate a new bromine radical. So, this can come around and do that whole first step all over again. With a new alkene and a new HBr, it'll do this cycle again and again and again and again. Every time it does the cycle, you get a new molecule of product. You consume two molecules of starting material. So it just keeps, it's a chain mechanism, right? It keeps chaining again and again and again. So those are all propagation steps. And then finally, you can get termination. Termination is when you have two radicals that come back together. So just pick any two radicals from above. Let's take I don't know, a Br radical. And let's take, I don't know, let's take one of the carbon-centered radical that's there. And if these two randomly meet, then you could get this molecule. And that molecule, by the way, it's like termination steps are ultra rare. And that's because the concentration of radicals at any point in time in a reaction mixture is going to be super low. So the chances, just statistically, of two radicals meeting and finding each other is going to be very low as well. So you're not going to get very much of that product. You're going to get a negligible yield, right? So technically you might find a little bit of it, but way less than 1%. It's not usually an important amount of that gets produced. The reason I pulled this out of chapter 9 and brought it in here is just because we're dealing with addition of HX and things like that to alkenes. So I just wanted to make very clear at this point that we have two types of HBr addition, Markovnikov and anti-Markovnikov. And the anti-Markovnikov way requires that you use peroxides. Great. Next. Also, okay, so we had two other ways of adding water, didn't we? We had 3 total. We had hydration with 50-50 sulfuric acid water that we just saw. Another way to do this, what number are we on anyway? 6, I guess this was 7. Let's go to 8. The next one was oxymercuration, demercuration. So that is when you have an alkene. Bring this one out. And this is a 2-step reaction. So this is when you have the 1 and the 2 on the arrow. It means there's like 2 separate, distinct reactions that you're doing. It's not like you just mix everything all in together. So the oxymercuration, demercuration starts with mercury 2 acetate. Lots of textbooks call it mercuric acetate, but that's an outdated name for it. IUPAC would say mercury 2 acetate. And second, there's a demercuration step that uses, I believe that uses sodium borohydride in water. So what this does is that overall, I'm not going to ask you to draw a mechanism for this particular one. What this does is it achieves the same thing as, no. It does Markovnikov addition of water across the double bond, just like you see here. And the beauty of this one is if there's possible rearrangements, you don't get them. Okay, so like if you had an example where you have this, and you try to do this with 50% H2SO4, you're going to get a rearrangement that produces this, which is something you should see if you can figure out why this is the product. I'm not going to do it. But if you use those conditions instead, then you don't have that. It just does Markovnikov addition. That's a chiral center. You're going to get a racemic mix. Generally speaking, as we saw in Unit 5, if you have achiral starting materials, you'll end up with optically inactive products. So they could be chiral, but if there is a chiral center made, like in this example, you're going to get a 50-50 mix, racemic mix, which is not optically active. Cool. So we have oxymercuration, demercuration, which was 8. The last one that we looked at was hydroboration, oxidation. I'm not going to draw that out. You can hear me. So hydroboration, oxidation looks like this, where you have an alkene, and we are going to use, again, it's a 2-stepper. BH3THF is one reagent that we sometimes see. Sometimes you also might see instead B2H6 diglime. They're equivalent as far as you're concerned. They're units of BH3. And the second thing we add here is H2O2, hydrogen peroxide. And we use usually base for this as well. This is a two-step one as well, just like making a cake, right? You bake the cake in step 1, you frost the cake in step 2. You don't mix the frosting in with the cake batter when you bake it. Okay, so what this does is anti-Markovnikov addition. Again, this is a chiral center. You would have racemic again, equal amounts of R and S, because there's no preference for which of the two faces of the alkene it adds to. The addition is syn. Unlike all the previous ones where you get a 50-50 mix of how it adds, this one is syn. So if you're on a ring, and you use those conditions down here, what you'll get like that. So the OH and the hydrogen end up cis to each other. The two methyls end up cis to each other in that product as well. They both add to the same phase. That's really the story there. All right, we're doing good. We're rushing through these. The next one is addition of halogens, addition of X2, which works with chlorine and it works with bromine. So let's use a little bit of a different one this time. This is, what, 3-hexene? And what we're going to react this with is Br2. And usually we use a nonpolar solvent. Hexane will work here. Often it'll use CCl4 in the book. That's carbon tetrachloride. Nobody uses that anymore. It's banned. That's the Montreal Protocol one. You might see it on tests or whatever, in books, old assignments, whatever. But yeah, hexane is probably more commonly used. If we use Br2 like this, the mechanism, we looked at this one, looks like that. So the Br adds to the alkene. You have two new bonds form, and the Br-Br bond breaks, and the pair of electrons in the covalent bond moves on to the other bromine. And what that produces is something that looks like this. Br plus, two lone pairs. That's called the bromonium cation. And you also get the Br minus produced. That cyclic cation thing is, not that stable. It's better than a carbocation, actually, but it's not that stable. And so what happens is this can react with one side, and you get Br on one side and Br on the other, and the addition is always anti. Okay, so the way this would react is, I guess, this would be coming forward, and then this one would be going back. So that ends up being a meso compound, because the Brs are trans, and when the ethyls are trans, and so that gives you a meso product. If you added it to the cis alkene instead, you get a pair of enantiomers. You'd get the RR and the SS. So anti is the key to that one. Always anti. Great. If you use this in a nucleophilic solvent, like a water or an alcohol, then you get a slightly different product. So let's, in this example, use cyclohexene, and we're going to do Br2. I'm going to make it methyl cyclohexene. Br2 in water. What happens is you get the bromine add, just like it did in the previous step, to give you the bromonium cation. This is water, right? So what happens is bromonium cation, plus you now have that methyl that's going out behind. And then we have water, which is, as we know, not not a great nucleophile, but it's a nucleophile all the same. High concentration because it's a solvent, and what it'll do is it'll attack the more substituted carbon here, because the more substituted carbon bears a greater amount of positive charge. Okay, so that goes there, that goes there. Generally, when you do SN2s, this is an SN2, it goes for the less substituted carbon. This is an exception. When the leaving group is cyclic positively charged thing, and there's examples at the end of Unit 10 that we skipped, it'll go for the more substituted carbon because there's more charge there. It's an exception to what we generally understand. So that produces a Br over here. It puts a methyl there. And the water has attacked from behind. And we know we don't like charged products, so we are going to bring a water in. And it's going to deprotonate that. To give you your final product. Br, HO. So we call these things vicinal halohydrins. The OH in the Br, that makes it a halohydrin. The halo is the H, or halo, I don't know. Hydrin is the water. Vicinal means they're on adjacent carbons. The OH and the Br are trans to each other. This is a chiral molecule, so you'll also get equal amounts of its enantiomer. 50-50 mix of the two. All right, we're doing great. That was 9. This one I guess we'll call 10. Kind of the same reaction. The nucleophile that comes in the second step just attacks the carbon that's more substituted. All right. 10, are we halfway through? We're halfway through our time. A little more than halfway through our time. Okay, what's next? We did a bunch of reactions. Okay, we did synthesis of cyclopropanes, or carbene addition was the next one. So there was 2 different sets of conditions for this. If you have pentene, and the other one was CH2N2 with either heat or light. H nu is light. If you have one of these conditions, what happens here, this is diazomethane. We talked about how dangerous this stuff actually is. It will lose nitrogen gas, producing a carbene, which is CH2 with a lone pair. And what that'll do is it'll add syn. Give you something like that. It'll give you a 3-carbon ring, cyclopropane like that. There was a related reaction we looked at that used chloroform, CHCl3, trichloromethane, I guess you might call that too, and some kind of alkoxide. Strong base. I think we use T-butyl peroxide just because, I don't know, T-butyl peroxide, not T-butyl, T-butoxide, sodium tertiary butoxide. The beauty about the T-butoxide is it's a very strong base, but it's not a good nucleophile. So it doesn't do as many competing reactions as a small alkoxide might. What this does is you get a reaction between the alkoxide and the chloroform to produce dichlorocarbene. And here you get a carbene with 2 Cls on it. So I'm going to bundle those 2 reactions together and call it a single one. Carbene addition. And there's kind of 2 sets of conditions to keep an eye open for. One that makes CH2, one that makes Cl2CH2, or CH2Cl2, whatever you want to say. All right, I think after this point, next was oxidative cleavage. And we did oxidative cleavage with 2 different sets of conditions. First one we used was ozone, and this is a 2-step one as well. And this creates something called an ozonide, and that requires a second step to break that up to give you the products. And the one that we were looking at was zinc and water. Probably the easiest way to do it. You could use dimethyl sulfide as well, which is stinky, so let's use zinc. What this does basically is, think about it as cutting that double bond in half and separating the two halves like that. Just cut it, separate them, and we're going to cap off each of those double bonds with oxygen atoms like that and that. It breaks the chain in two. In this case, it gives you an aldehyde and a ketone. That's always the products, aldehydes and ketones for this one. We looked at a variation of this. Instead of using that, if you used KMNO4 with base, like KOH, water, and you heated the thing, do it hot, this will do a cleavage too, but this is a little more aggressive. And this will also oxidize CHs. So what it would do in that example, again, it breaks the bond. The left side, though, becomes a carboxylic acid, and the right side becomes a ketone. The way that reaction works is if you have a CH2 on one side, that becomes CO2. If you have CR2, that becomes a ketone, CRROH, or O. And if you have a CRH, that becomes a carboxylic acid. So all kinds of different products you get with that one. You can't get aldehydes from that one. Aldehydes will oxidize further and give you carboxylic acids if you use KMNO4. That's oxidative cleavage of those things. While I'm here, let's do oxidative cleavage of alkynes. They'll react under the exact same conditions as before. And what these will make, exact same conditions, KMNO4 or ozone, it will break that and make 2 carboxylic acids. So you get 2 molecules of acetic acid out of this one here. Cool. I'm still numbering. I'm on 13. The next one was synthesis of vicinal diols. And we had 2 sets of conditions for this one as well. If you have an alkene, and the first set of conditions, I believe, was, again, the KMNO4 with KOH or NaOH, some base, water, but you got to keep this thing cold, right? So if you keep it cold on ice, for example, so it never gets too hot, it instead of ripping the thing apart like before, what it will do is make a diol. And the reaction is syn. And again, for this one, you don't need to show me a mechanism. The other version of this used osmium tetroxide. And what went with the osmium tetroxide? I think was this a 2-stepper, and the other one was... See, now I forget. And I expect you guys to know what it is too, right? So here's my advice if this happens to you on an exam. I forget which conditions go there. Look around on the exam and find the same conditions drawn somewhere else. Here's something I'll promise you. I'm not going to incorrectly write the conditions for any reactions on the final exam. So it's not like I'm going to try to trick you. Is this right or is this right? Like, no. Any chemist who's actually doing one of these reactions in the lab isn't just going to do it blind. They're going to look up a procedure beforehand. So it's important that you know, but the nitty-gritty details of what is required for the reaction, you're going to double check that with literature preps before you do it anyway. So yeah, I think it's NaHSO3. That's my guess. But I have my phone right here, and I can double check. Oh, I'm right. There we go. Sometimes a good guess works out well. We use pyridine as well in that first step as the solvent. Pyridine is that one that looks like, same product by the way, as above. Pyridine looks like benzene, but it's got a nitrogen in it, which makes it smell bad, and it makes it act as like a weak base, so it can absorb strong acids that could produce in a reaction like HCl, HBr, things like that. All right, what else do we have in this unit? Scraping the barrel now. There's a couple of reactions that were like the previous reactions but on alkynes. So one of them was addition of X2, like Br2 or Cl2. This will add once. You can stop it there, or you can add another one. To make a tetrabromo alkane. You can add it twice. We also looked at addition of HX, something like HCl, and this will add like that. And you could add a second one, and I believe they both add same side to make a geminal dichlorodihalide. All right, I'm going to just use my cheat sheet here to see if there's anything I'm forgetting in this unit. Oxidative cleavage, halogenation, addition of HX, oxidative cleavage. I think I got them all. Cool. So that's unit 8 done, plus we borrowed one already from unit 9. So with the remaining time, we're going to look at the reactions from unit 9 and unit 10. And we've already finished one of the unit 9 ones. And this is a very short chapter. This is the radical chapter. And the first one we looked at was radical halogenation. We said that if you have, what number am I on, 15? If you have an alkane where all of the hydrogens are equivalent. So this would be an example where if you ran a carbon-13 on this, you'd just get one peak. And you use Cl2 with either heat or light. H nu is the symbol we use for light. This will produce Cl. And we said the Cl will go in a random position, more or less random. It has a slight preference for different types. Yeah. Yeah. So what that symbol is, it kind of looks like a V, but it's not. It's almost like a scripty V. It looks like that. That's actually a really good drawing of nu. It's the Greek symbol N. Yeah. And with COVID, you're learning all the Greek letters one by one. Yeah. We're on Omicron, or however you say it. So that comes after nu. So nu, there must have been a nu variant at some point. Oh, really? They skipped nu? They skipped nu because, oh. Oh, I would have welcomed that. Oh, well. So chlorine is very aggressive. Chlorine is not very selective. It'll kind of go wherever. And so the mechanism for this reaction is the heat or light will cause the chlorine to undergo homolysis. So your initiation step is Cl, Cl. And the bond breaks. You get 2 chlorines, radicals. And then these are they're hungry for electrons. And they'll take them where they can find them. There's no alkenes here, no double bonds, so no juicy pi bonds for them to take electrons from. So it does what it can. I'm going to change the molecule here just so I don't have to write so much to methane. We're going to simplify this thing. So we're going to take methane and chlorine. And what happens is one of the bonds splits. One of the electrons goes with the electron from chlorine. The other one goes onto the carbon. And you end up with the methyl radical plus HCl. And this is a propagation step because you start with a radical and end with a radical. Next, that methyl radical can find, by random collision, another Cl2 molecule which can do this. That makes your product CH3Cl plus a new chlorine radical. So these are propagation steps, both of them. Finally, you have termination steps. Typically what I'll ask on an exam is draw an example of a termination step. You don't have to draw all possible termination steps. So just pick any two radicals that you want. They could be the same, they could be different. Let's pick two methyls plus another one. If in the unlikely event two of these collide with each other, they'll terminate to give. But again, the products of termination steps are like super low yield. You don't have to worry about them. All right, so unit 9, we did this unit, this reaction. We did addition of HX. Is that all? Oh, yeah. There's also bromination. So if you do this same thing with Br2, doesn't work with F2, it's too vigorous. It doesn't work with I2, it's too sluggish. But if you have Br2 in the presence of lighter heat, there's a better new there. What it'll do is the exact same mechanism, but this one is a little more selective. And it'll hunt down tertiary centers. The major product will be reaction at a tertiary carbon to give you a tertiary alkyl halide. So that's good if you want to do like SN1s or E1s or something like that, where you need a tertiary to give you a carbocation. That's a good choice. So Br2, Cl2, they do the same thing, except Cl2 is sort of indiscriminate and will go everywhere. Br2 is selective because it's less reactive, more stable, and it'll go for tertiary centers. I think that was it. We looked at a few other things in Unit 9. We looked at radical polymerization. I said I'm not going to test it. We looked at oxidation of alkenes in membranes. You know, we talked about antioxidants and things like that. Not going to test you on that either. So I think that's it for that unit, which moves us into Unit 10, and we have 6 minutes. I think we can get Unit 10 done in 6 minutes. 16, we looked at conversion of alcohols to alkyl halides using PX3. Use a chiral alcohol here, and we said that if this reacts with PCl3 or Br3, there's a two-step mechanism that happens where that attacks. You end up getting chloride comes off at the same time. It's like an SN2. Plus Cl minus, that's a plus charge there, by the way. Cl minus. And this will attack the carbon and knock that thing out. And end up, because it's backside attack, it does an inversion because it's SN2. And then you get this thing, you know, PCl2 with an OH on it. And then this can actually continue to react 2 more times. So you get 3 equivalents for each molecule of PCl3. But anyway, what this does is it converts the alcohol to an alkyl halide. This was preferred over HCl in many cases because you don't lose your stereochemistry, first of all. No carbocation. You instead invert it. which keeps it. It just inverts it. Also, because there's no carbocation here, you get no rearrangements. So this, is preferable to the same reaction with HCl in many examples. HCl would give you the same product, but it would give you a racemic mixture. Okay, 17. I think, by the way, we said you could get PCl3 and PBr3, and those are the only two. PI3 and PF3 aren't options here. That's a recurring theme. Fluorine is weird. Like every example we use with the halogens, fluorine doesn't work. Where iodide sometimes doesn't work. It's just a little bit too lazy sometimes. Okay, we also did protecting groups. I'm not sure if this is the right order, but we protected alcohols and then deprotected them. And the reason we did that is so that they could survive some other reaction. So for example, if you have that reaction with HCl and you wanted this product, we said, that's not going to work because it's going to react with both the alkene and the OH. It's going to do substitution and addition. So instead, what you can do is protect the alcohol using TBDMSCl, and I believe imidazole was the base that was added with it to sop up HCl. And that basically makes that thing unreactive. You can do your chemistry on the other group. You can do any of the addition reactions that we've seen in Unit 8. And then we could deprotect it later using a fluoride source, which was normally TBAF, tetrabutyl ammonium fluoride. And THF was the solvent that we often use there. That just takes it back off again. So we talked about this as it's like throwing a tarp over part of the molecule to protect it, and then you pull the tarp off when you want it back again. Okay. TBDMS actually is like strong acids can deprotect them too. So maybe addition of HCl isn't the reaction we want to protect against. But as far as you're concerned, it'll protect against any reaction except reaction with TBAF. All right. The last piece, I think the last piece in Unit 10 was mesylates, triflates, and tosylates. Was turning alcohols into good leaving groups. We said if you tried to react this with sodium iodide in acetone, you get no reaction because you don't have a leaving group. You can't do an SN2. These are SN2 conditions. But what we can do is convert that into a good leaving group using methane sulfonyl chloride or toluene sulfonyl chloride or trifluoromethyl sulfonyl chloride. So this would look something like TFCl, and I think we use pyridine here. And what that does is make the triflate. This then will react in an instant it turns the OH into an excellent leaving group under very mild conditions. We saw that you can turn it into a leaving group using strong acids, H2SO4, HCl, HBr, HI, back at the beginning of Unit 8. But that wouldn't work if you had, for example, an alkene on it, because that'll do addition there as well. So instead, what we're going to do is use, turn it into a leaving group in a different way as a sulfonate ester. So the three that we used were TFCl, MSCl, or TSCl. This is triflate, mesylate, and tosylate. As far as you're concerned, these are all equivalent for this course. Triflate actually is the best leaving group out of the bunch of them. Tosylate is next. Mesylate is the next two. But all of these are excellent leaving groups. All of these you can consider equivalent to iodide. So any reaction you'd have of an alkyl iodide, if you replace these, if you see that, think of this molecule. It's essentially how that's going to react. It's going to be a very good leaving group. All of your reactions that had iodide, where iodide leaves as a leaving group, these sulfonate esters will do the exact same thing. I think we got them all. And it's exactly 9:20. Well, it's 9:21 now, but we're pretty good. All right. In Monday's class, what we're going to do is example questions from old exams. If there's any you want to see in particular, send me a message.